A signal is repeating across our planet, and what it's revealing about our interstellar visitor changes everything. Over a span of just 7 days, skywatchers from 3 separate continents pointed their instruments at the same mysterious object. The data from Spain, Thailand, and Norway didn't show the chaos they anticipated. Instead, they recorded a pattern of disturbing stability. At its heart, the core remained stubbornly intact. It didn't fracture or blur. It held a perfect, round form, as if anchored by unseen forces. The halo surrounding it expanded, the leading edge sharpened, and the tail developed a gentle, coherent twist. When astronomers compared notes, the alignment was impossible to ignore. 3 distant points on Earth, 1 sky, and a story that was no longer following any known script. The solar encounter that should have broken it seemingly made it more defined. This has prompted a silent, more profound shift in the scientific dialogue. If this isn't decay, what phase is it entering? Before these images surfaced, the tale of interstellar object Atlas seemed clear-cut. It arrived from beyond our solar system on a trajectory steeper and faster than local bodies. Its scale immediately set it apart. Most extrasolar wanderers are tiny and volatile, but this one presented a substantial, brilliant profile, placing it in an exceptionally rare class. Consequently, many research teams predicted it would not endure its close solar pass. The logic was straightforward. A massive icy structure subjected to extreme stellar heat typically splinters, ejects matter, and loses its fundamental shape. Early data even hinted at this fate. As monitoring refined, telescopes detected minor flickers in luminosity. Some read these as evidence of mounting internal pressure, a prelude to a rupture. Official statements cautiously noted the nucleus could become unstable at the peak of heating. These weren't alarmist claims, just standard scientific forecasting for an unknown body meeting solar radiation. At that juncture, nothing indicated Atlas would deviate from the typical narrative. This expectation created a unified atmosphere across global observatories. Professionals and amateurs alike were poised to witness a dissolution. Major facilities prepared to document the anticipated cracking, fragmentation, or a sudden dimming. Every few days, new simulations populated online forums, projecting how much of the visitor might remain post-encounter. The figures differed, but the underlying assumption did not. It would not hold together. As Atlas neared the sun, scrutiny intensified. Observation schedules were expanded. Telescopes hunted for the earliest markers of catastrophic failure. The prevailing theory was that the thermal spike would compel the nucleus to come apart. For weeks, the anticipation was for a flattening brightness curve, a distorted silhouette, or a tail scattering in erratic directions. But none of those predicted signs materialized. The first confirmed data after the solar encounter delivered a result nobody had forecast. The core, expected to be compromised, maintained its geometry. The object presumed to be destabilizing appeared virtually unaltered. Observers saw no evidence of a shrinking form or a splintered heart. They witnessed a consistent spherical center displaying zero indications of impending collapse. That was the pivotal moment. The narrative constructed over months no longer matched the reality overhead. And from that point forward, each fresh observation pushed Atlas further from the model everyone had prepared for. The first major clue of this shift originated in Spain. On November 22nd, a sequence of crystal-clear images captured Atlas with a degree of precision that startled experienced analysts. When they magnified the object center, the brilliant core appeared almost mathematically exact. It didn't lean or smear into multiple nodes. It maintained a single sharp pinprick of light, positioned with perfect symmetry within its glowing envelope. This was anomalous for a key reason. When a cosmic body begins to fail, the earliest warnings manifest in its symmetry. A failing nucleus loses equilibrium and starts to tremble. The radiant center drifts off axis, and the contour grows lopsided. If fragmentation is beginning, the core becomes irregular long before any piece separates. This sequence has been recorded for decades in comets and icy asteroids, which is why researchers took immediate notice when the Spanish data displayed none of it. Instead of distortion, the object looked more refined. The circular boundary held firm. The intensity profile rose smoothly, without erratic peaks or troughs. They expected turmoil after the solar close approach. The Spanish imagery presented the inverse. The more active Atlas became, the more steadfast its core seemed. This detail spread rapidly through astronomy networks. Experts pored over the frames, contrasting them with earlier sequences. They anticipated finding subtle asymmetries missed in the first review, but the collective verdict held. The symmetry was real, and it was profound. Even after filtering atmospheric interference, the central point remained fixed. It behaved like a governed structure, not one nearing its end. For many, this was when the earlier forecasts began to crumble. The body predicted to warp under heat showed no strain. Instead, stability increased as peripheral activity amplified. The tail lengthened, the halo swelled, yet the core held its position without deviating a fraction. This prompted a new line of inquiry. If a body is being acted upon by heat, jetting, or internal pressures, its center should shift. The Spanish data implied a different mechanism. Something was maintaining the core's alignment. Something was preventing even the slightest tremor. And this leads to the critical quandary from the Spanish observation. If natural forces don't preserve such perfect circularity, then what precisely is holding the core of Atlas in place? If Spain exposed the core's precision, Thailand uncovered something even more startling about its luminous shroud. The night of their recording, conditions were less than ideal. Clouds drifted through the field of view, and a humid haze softened the scene. Yet, despite this, the footage still revealed a pattern too ordered to dismiss. Around Atlas's center, the halo constituted a near-ideal circle, so distinct that amateur skywatchers spotted it instantly. The most striking element was the halo's behavior during brightness surges. Instead of illuminating as a uniform mist, the light seemed to intensify in discrete tiers. Each tier arced around the core like a slender ring, sketching the impression of stacked, concentric shells. These shells formed and dissolved with remarkable regularity, as if the object was emitting material in timed pulses. It bore no resemblance to the chaotic, uneven outbursts typical of an active comet. The rings maintained a morphology hinting at a rhythmic cycle. Analysts well-versed in atmospheric distortion examined the footage, presuming the rings were mere visual artifacts. But upon enhancement, the pattern persisted. Even through the haze, the halo's edges stayed smooth, and the outer layers kept their equidistant spacing. The clarity wasn't as pristine as Spain's, yet the overarching structure matched in a manner that felt beyond coincidence. Both showed a stable center. Both displayed circular borders without warping. And now, both indicated a layered luminous envelope suggesting regulated emission, not random shedding. For two disparate regions with wholly different weather to capture identical architecture raised a question that couldn't be easily sidelined. This consistency was unusual for another reason. Interstellar objects are inherently erratic, especially when engaging with the sun. Their halos typically fracture into visible gradients that shift based on viewing angle, temperature, and local jet activity. Yet in Thailand's recording, the rings preserved their spacing as the object flared. Even the outermost shell held a gentle curve, as if adhering to an internal clock. The correlation between these datasets steered the discourse down a new path. If one location witnessing a perfect halo is chance, and two is coincidence, then identical structural patterns across continents propose something far more significant. This leads to the central puzzle from the Thailand footage. If Atlas is truly a runaway interstellar fragment, why are observers on different continents seeing the same uniform, layered halo shaping itself identically at the same time? While Spain and Thailand centered on the core and halo, Norway introduced a completely different detail. Their late-night polar observations captured Atlas's tail with unprecedented clarity. Under the stable Arctic sky, the tail didn't stream out in a clean, straight line as comet tails normally do. Instead, it carried a faint, seamless twist that curved along its length, creating the impression the entire structure was slowly revolving. This twist is significant because a comet's tail usually mirrors the direction and push of sunlight. When material escapes the surface, the solar wind drives it outward in a direct line. That's why most comet tails remain linear, pointing directly away from the sun. The Norwegian footage revealed a divergence. The tail didn't diffuse evenly. It arced and coiled in a shallow spiral, akin to a thread following a turning spindle. Observers started contrasting this twist with documented patterns. If a body is spinning, the gas it ejects will curve as it travels outward. If the ejection is irregular, the bend becomes more pronounced. Both interpretations point to internal motion over random solar pressure. The fact that twist repeated across multiple frames made it difficult to write off as atmospheric blur or lens flaw. The imagery also connected to an earlier scientific note.
NASA had previously verified that Atlas produced a sunward jet, meaning some material was being expelled toward the sun, contrary to typical comet behavior. A jet pushing sunward already signals something odd about the object's internal dynamics. When Norway's visuals showed the tail curving in a controlled spiral rather than a simple outward stream, the link grew more compelling. Analysts observed that a twisted tail could mean the object is rotating in a steady rhythm. The curvature wasn't severe enough to imply violent motion, yet it was sufficiently clear to indicate that gaseous release was not uniform across the entire surface. So, what are we looking at? The evidence is building from every corner of the globe, painting a picture that defies our standard models. It's a story still being written in the silent language of light and motion. For more deep dives into the universe's greatest mysteries, make sure you're subscribed to Winds of Thought. And if this investigation made you think, hit the like button. It truly helps us continue this work. The sky is showing us a pattern it wasn't supposed to. Stability, not chaos, is the real mystery here. The latest data has arrived, and it confirms our interstellar guest is doing something no comet ever should. Something was directing the outflow. At a minimum, this indicated the object known as Atlas was not acting like a fragile, disintegrating body in its death throes. A nucleus on the brink of destruction would never sustain such a smooth, repeating curvature in its tail. With the Norwegian findings now part of the record, astronomers confronted 3 distinct observations, each pointing toward coordinated activity. A core that refused to budge, a halo assembling in distinct tiers, and now a tail spiraling as if sculpted by the object's own rotation. This leads directly to the puzzle at the heart of Norway's discovery. If the tail's spiral isn't being carved by solar wind alone, then what force is guiding the motion behind Atlas? When the initial wide-field images from Virginia arrived, they inserted another unforeseen element. Unlike the focus shots from Spain, Thailand, and Norway, these observations captured a much broader celestial view. That expanded perspective uncovered something remarkable. The tail-trailing Atlas extended further than in any prior recording. It swept across the image in one continuous, elegant arc, implying the object was emitting more material than ever. To many, this resembled the onset of a major eruption. But the shock wasn't the tail's length. It was the core's conduct. Even as the tail stretched into the void, the central point of light remained unaltered. It didn't wander, deform, or smear. In fact, when analysts magnified the core, it looked nearly identical to earlier datasets. The surrounding halo had broadened, and the outer radiance had intensified. Yet, the bright, spherical shape at the center maintained the same exact symmetry. This sequence defied standard astronomical expectation. A powerfully lengthening tail usually signals unstable activity within the nucleus. When gas release becomes violent, it disrupts the core from the inside. Pressure pushes asymmetrically, forcing the center of brightness to stretch or migrate. The object might develop a wobble or sprout multiple bright spots as fissures emerge. That's the textbook behavior for comets undergoing intense outgassing. Virginia's imagery displayed the reverse. The tail grew more prominent while the core stayed utterly motionless. It appeared almost anchored in position, like the immutable hub of a widening wheel. Even as the halo gleamed and the outer haze disseminated, the core continued to sit precisely where it had been before, steady and distinct. Observers logged this as one of the most jarring contrasts in the entire monitoring period. This provoked an unavoidable question. If the object was losing material rapidly enough to forge a longer tail, why was the core not responding? Why was there zero indication of stress? The dichotomy between vigorous external expansion and profound internal stillness didn't align with the standard profile of a body under thermal duress. Instead, the pictures implied a phased process, with the core preserving its integrity while its surroundings transformed. By the time supplementary frames were studied, the inference grew more difficult to reject. Something about Atlas was transitioning, but not in the destructive manner everyone had predicted. The behavior in Virginia's footage made it seem more like an orchestrated shift than a chaotic breakdown, and that introduces the central turn. If the stable core and expanding outer layers are part of a sequence, then is this stage 2 of a larger metamorphosis now playing out around Atlas? By the time information from 4 global regions was cross-referenced, an even stranger pattern emerged. When astronomers track an object destined to fragment, they anticipate seeing the same progression every time. The initial warning is a loss of symmetry. The glow moves off-center, the form turns irregular, and the core drifts as internal pressure mounts. The second sign is the emergence of multiple bright peaks, caused when internal cracking creates new active zones. Finally, the tail starts to distort, bending into erratic kinks as fragments tug in slightly different directions. Atlas demonstrated none of these behaviors. On the contrary, each new observation revealed the opposite trend. The object grew more uniform, more circular, and sharper in outline. Rather than splitting into several light sources, the core stayed singular and centered. The halo expanded, but kept its architecture. Even the layered shells captured from Thailand maintained a spacing too regular to match the initial stages of disintegration. What witnesses were documenting wasn't the disorder of a failing nucleus. It was the coherence of something preserving its form. One detail advanced this distinction further. The unusually elevated carbon dioxide readings underscored how different Atlas already was from common solar system comets. CO2-rich objects tend to behave erratically, often fracturing quickly when blasted by intense sunlight. But instead of weakening, Atlas grew more stable in appearance as its activity escalated. The more gas it released, the more defined its core became. For some researchers, this prompted a fresh consideration. If an object predicted to break apart instead enhances its symmetry, perhaps something internal is assisting it in maintaining shape. The concept doesn't demand exotic assumptions. Even in natural bodies, certain forms of layering or internal reinforcement can regulate how material escapes. But the degree of stability witnessed in the Atlas implied more than simple ice and dust. It hinted that the nucleus might contain an unidentified structure, something channeling the gas release while preventing deformation. This perspective shift altered how many viewed the entire episode. The query was no longer about when the object would collapse, but why it was resisting collapse so effectively. If the core stayed centered under mounting stress, then whatever lay inside was operating differently from known examples. And that leads to the pivotal twist of this analysis. If Atlas is not behaving like frozen stellar debris, then we face a more difficult question. If it isn't just ice and rock, then what is it truly composed of? As independent observers correlated their footage, major observatories began disseminating updated measurements. The James Webb Space Telescope was among the first to deliver a sharper analysis. Its data showed a remarkably consistent emission pattern originating from Atlas. There were no erratic flickers hinting at internal chaos, no sudden brightness dips, and no irregular pulses that typically herald a failing core. JWST's findings suggested the object was holding itself together more effectively than projected, even as solar radiation intensified during that window. This steadiness garnered attention because such stability is rare in objects that have just endured a close solar passage. Hubble's observations added another dimension. While the halo continued to enlarge, completely normal for an active interstellar body, the core itself did not move. It didn't flatten, elongate, or produce multiple light peaks. It remained centered in every single frame, even as the surrounding glow strengthened. For an object supposedly under thermal stress, this level of consistency was immediately conspicuous, bolstering the idea that whatever was happening inside the nucleus was unusually controlled. NASA's internal annotations, referenced in public briefings, emphasized three particulars. The first was the object's substantial size. Compared to prior interstellar visitors, Atlas appeared unusually large, which should have made it more susceptible during its solar encounter. The second was its carbon dioxide concentration. Levels noted in research preprints fell outside the typical range measured in solar system comets. The third was its trajectory. Instead of passing through at a random angle, as most interstellar objects do, Atlas traveled almost perfectly along the ecliptic plane, for a planet's orbit. That alignment is statistically improbable and continues to perplex mission analysts. Another unanticipated clue came from repeated detections of a sunward jet. Material was being expelled toward the sun, a behavior seldom observed and hard to explain with standard models. A jet like this should have destabilized the nucleus. Yet, the core displayed no sign of tension or imbalance. Instead, the jet seemed to operate in a steady, cyclical manner, almost as part of a larger pattern rather than a chaotic gas release. When these datasets merged, JWST's stable emissions, Hubble's fixed core, NASA's anomalous CO2 levels, the improbable orbital alignment, and the recurring sunward jet, the conclusion grew more inescapable. None of the indicators pointed toward collapse. None matched the early forecasts of a body losing structure after its solar pass. What they pointed toward was something else entirely. Across every instrument, every region, and every wavelength, the data leaned the same way. Atlas was not coming apart. It was transforming.
and it was following a pattern far more consistent than anything expected from an interstellar fragment. By the conclusion of this observation series, the most startling pattern is also the toughest to dismiss. The more active Atlas becomes, the more stable it appears. Its halo widens, its tail reaches farther, and its emissions gain strength, yet the core stays centered, steady, and nearly identical. This contradicts every expectation for an object under immense stress. Typically, rising activity signals an approaching breakup. Here, the opposite keeps occurring. Across 4 locations, Spain, Thailand, Norway, and Virginia, the same behavior surfaced repeatedly. Each region unveiled a different piece of the puzzle, yet all directed attention toward the same structure transition. A perfectly round core, a halo forming in layered rings, a gently twisted tail, a balanced heart within an expanding system. The continental consistency sets Atlas apart from any standard disintegration scenario. Instead of unraveling, the object appears to be reconstituting. We are not watching an end, but a transformation. Scientists worldwide now await the next cycle of high-resolution images from NASA and partner telescopes. Those observations may reveal whether this stability is temporary or if the object is entering a novel phase entirely. Researchers hope upcoming data will expose subtle core changes or new halo features earlier images couldn't resolve. For the first time, the question surrounding Atlas is pivoting away from its survival and toward its fundamental nature. If 4 nations documented the same progression, and if major instruments keep confirming the same signals, then the mystery extends far beyond the predicted behavior of a typical interstellar visitor. The early fragmentation forecasts no longer fit the evidence. Every dataset now suggests a larger, more synchronized transformation that challenges long-held assumptions about how such objects evolve under solar influence. And that leads to the question concluding this chapter. Are we simply observing a comet, or are we witnessing a natural process without direct parallel in our solar system? Share your perspective below. For more explorations into cosmic mysteries, make sure you're subscribed to Wines of Thought. If this analysis made you reconsider what's possible, please hit the like button. It genuinely supports the channel.